All right, welcome back, everyone. Thank you for joining today. So, we were discussing trajectory data of obstructed traffic flow. This is section 3.2 in our exercises for trajectory data chapter. And we had covered the first 6 questions here. Question number 7 is about travel time delay. So, what travel time delay is imposed on a vehicle entering the scene at t equals 20 seconds and x equals negative 80 meters? So, negative 80 is right here. So, this is the location, and t equals to 20 seconds is here. So, you're essentially looking at this trajectory. And for this trajectory, the question is, what is the travel time delay? So if there wasn't any um, traffic light here, then this trajectory would have maintained its current speed and there will be no delay. So if we draw a line using the same angle here, then it's about 40 seconds when the trajectory would have been completed within this spatiotemporal region. So that's 40 seconds. But this trajectory actually ended here, which is about, I would say, 68 seconds. So if it is 68 seconds and this is 40, then the difference between them is 28 seconds. So that's what I would say is the travel time delay. Let's see what the answer is. By the way, at any point, if you have any questions or you want to interrupt, please let me know. All right, so here it says without the red light, the vehicle entering at x equals negative 80 meters and t equals 20 seconds would have reached the end upper border of the diagram at t end equals 38 seconds. De facto, it arrives at x equals 100 meters at time t equals 69 seconds, thus delayed by 31 seconds. So my estimation here was 28 seconds. They estimated 31 seconds. So I think it's close. Now let's see the final question in section 3.2, which is number 8. Find the acceleration and deceleration values, assuming they are constant. The start of the acceleration phase and the end of the acceleration phase of each vehicle are marked by dots. So the red dots and the blue dots that we see on this figure, they indicate the start of the acceleration and the deceleration. So here we have the red dots. This is where before that vehicles were moving at a constant speed, and after these red dots for each vehicle, we have deceleration starting, and then eventually here the vehicle completely stops. In this case, the vehicle starts accelerating at this point, and then after the blue point, they maintain their speed. So acceleration is happening here and deceleration is happening here. So the question is, what is the constant rate of deceleration and acceleration? So if you look at any of these points, for example, if you look at this one, this is starting at minus 80 meters and then ending at almost, I would say, minus 60. So this is a distance of 20 meters. So 20 meters divided by the time that it's taking them to completely stop. So this is about 38 seconds. And this is very close to, or we can actually take this as 40. So this is 40 seconds. So it's about 2 seconds. So that would be 10 meters per second. That's the speed. And then here they go to completely stopped. So they're moving at 10 meters per second and then completely stop. So that does give us speed, but that does not tell us about um, acceleration or deceleration directly. But there's another way in the, actually, let's look at the solution. 674, I guess. So here they say in 8, the braking distance is 25 meters, while the distance covered during the acceleration phase is 50 meters. Let's first focus on the braking distance. So the braking distance in this case, I found this to be about 20 meters. They are saying it's 25 meters. So based on that, if the braking distance is 25 meters, we can use the equation of motion. That's what they have used here to estimate the acceleration rate. So if we try to do that, so equation of motion would be 2as is equal to v squared minus u squared. So in this case, let me quickly check the formula here. So this is positive acceleration. This is the distance. V is the final speed and u is the initial speed. This is from the equation of motion that we have studied in high school. So if we take, if we want to estimate the acceleration, and we know that in this case, there is an initial speed, but there is no final speed. And for deceleration, if we use b, then b is minus a because it is deceleration. In that case, this would be u squared minus v squared. And we know that the initial speed is 10 meters per second. So it's 10 squared, and final speed is going to be 0. So this would be 2 into the distance that is covered, which is 25 meters in the book. And here we are doing b. Is that correct? 10 squared divided by 2 into 25. So they get 2 meters per second squared. So if we estimate that, so this is 100 divided by 25, that comes out to be 4. 4 divided by 2 is 2. The b is 2 meters per second squared. And if we do the same thing for acceleration, 2as equals v squared minus u squared, then we get 1 meters per second squared for acceleration. Any questions about this?
Can you highlight like how we get like the braking distance and the distance for the acceleration, and also like the changing time they took they have got 10 seconds. In our case it's like 2 seconds.
Yeah. So if we focus on any of these trajectories, so I considered only this one for now. And if you look at the time here when the vehicle entered, this was in my approximation about 38 seconds. And this is 40 seconds, as you can see here. So the difference between them in terms of time is 2 seconds. And if you look at the distance, this is minus 80. And this, in my approximation, is about 60, but it may not be. It may be 55. If we take something like this, yeah, this may be about 55, minus 55 meters, because 60 is in the middle of 40 and 80. This is 40 meters. So the half of it would be 60, and just above 60 would be about minus 55. So this point is minus 55. So if this is minus 55 and this is minus 80, if we ignore their signs and we deduct that, this comes out to be 25. So that's a 25 meters distance for the braking. So here's the braking distance that they mentioned. So once we have that, we can now use the equation of motion. And if we quickly search for it, then this is the equation that I was sharing before. V squared equals to u squared plus 2as. V is the final speed, u is the initial speed, a is acceleration, and s is the distance that is covered. So if we rearrange that, we can rearrange it like this. 2as is equal to v squared minus u squared. A here is assumed to be positive, it's the acceleration. But since we are looking at the braking distance, so starting from this red point, deceleration starts. So deceleration starts and then eventually you stop. That's why the trajectory is horizontal. So this is negative acceleration or deceleration. So we um, plug in that here. And since b is negative a, we rearrange the equation and we get u squared minus v squared. So u squared is the initial speed. In this case, we know that the initial speed is 10 meters per second, because if we take the gradient of this trajectory, that comes out to be 10. We have done that right here. So this is about 20 meters divided by 2. So instead of 20 meters, you can use 25 meters. So 25 divided by 2 would then be like 12.5 meters per second. So if we use that here, 12.5, and we have 2 into the distance that is covered, 2 into 25, then let's see what we get. So we have 12.5 into 12.5 divided by 25 divided by 2. So this comes out to be about 3 meters per second squared. What they found there was 2 meters per second squared. If we assume that the distance is like 20 meters, then this comes out to be 2 meters per second squared. So that was the distance that we obtained for the deceleration. For acceleration, we can again use any of these trajectories. So this is the point where acceleration has stopped. This is the point where acceleration has started, because remember, this is where vehicle was completely stopped. Then it started to speed up. And then at this point, which they conveniently labeled for us in the book, we know that acceleration has stopped. And now after this acceleration is going to be zero and vehicle is going to maintain its speed. So based on that, what we are interested in is to determine what is the uh, time here and here. Similarly, what is the distance here and at this point. So if I draw lines for that, then this distance may be 10, and this may be, let's see, slightly above 40. This may be 45. So 45 here, and this is 10. So then the distance of acceleration is 35 meters. Let's see what they have mentioned here. They say it's 50 meters. So my approximation is not correct. This distance should be 50 meters. Yeah, roughly if we look at zero, the line of zero here, and this is above 40, this may actually be 50, not,
Yes.
it may be 55 or something. So then we get about 50 meters, and this may not be 10, this may be smaller, this may be 5 meters. So that gives us, I think, the question that you answered, that gives us the answer to that. The distances for acceleration and deceleration. And plugging those values in the formula for equation of motion, you get these acceleration and deceleration values. All right, now the final section before we go to the next chapter is trajectories of city traffic. Given are the trajectories of the second lane of a four-lane directional road in a city. This is from Lancashire Boulevard, which was the data for which was gathered for NGSIM project. So we have these three colored trajectories for three different vehicles. Question is, at which locations do you expect signalized intersections? Also, estimate the red phases of each traffic light for vehicles in the direction of the trajectories. Let's start with the first part of the question. At which locations do you expect signalized intersections? So we see that vehicles are stopped at different locations. Let me actually take this into Paint and then let's go. We can annotate this figure there. So we have this point where we have vehicle stopped. Then there's this point, and then there's also this point. So it does seem that there are these three different locations where vehicles have stopped for some time. And so that indicates these are likely the intersections where vehicles are stopped. So this is roughly at 50 meters, then at about 250 meters, and then 350 meters. So that would be the answer to the first part of the question, where we expect signalized intersections. The second part says also estimate the red phases of each traffic light for vehicles in the direction of the trajectories. So if we want to estimate the red phase, we can look at these times. So this is 320 seconds, and this is 380 seconds. So this is a total of 60 seconds. Okay, I heard something. Let's go back. There seems to be 60-second red light phase, at least for this intersection. For this one, this is also starting at 320 and ending at almost 350. This one seems to be 30 seconds. Let's see. So this is question number one. There it says signalized intersections are expected to be a little bit downstream of the vehicle stopping without a leader at about 50 meters, 250 meters, and possibly 355 meters. So 50, 250, and 355. So we guessed it correctly. And then the red phase starts when the first leader about to stop behind the traffic light begins to decelerate and ends a little bit before the first vehicle starts to accelerate. That is between 350 and 317 seconds at x1. So at x1, which is 50 meters, it says 350 and 317, so just before that. So roughly 30 something seconds. And then for x2, it's 317 to 378. Again, 317 somewhere here to 378, so just before this point. That comes out to be roughly 60 seconds also. And then they have also provided us with the red phase for the third one. All right, let's go to the second part.
Before we go to the second part, at x equals 200, there are horizontal stationary lines. Are we not going to consider them as traffic lights for the red and the black?
At x equals to 100,
200.
at 200, right here. So I think what is happening is that the traffic light is here, right? And this is the first vehicle that stopped. And then these are the followers of this vehicle. This is the first follower, which is also stopped after this. Then the second one, which is stopped after this, and so on. So because we don't see any trajectory before this trajectory, that indicates that this is the very first one that is stopped after the traffic light, or sorry, just before the traffic light. All others are stopped behind this first leader. And the same applies here. This is the first leader, and then this is the first follower. Similarly here, this is the leader, and this is the follower, this is another follower, and so on. So because we don't see any trajectory or before this, those are the leaders which are stopped just before the traffic light. So I think that answers your question. These are not locations of the traffic lights. These are just vehicles stopped behind the leader. Okay, so question number 2 is some trajectories begin and end inside the displayed spatiotemporal window, and this is not a data error. Give 2 possible reasons, each for beginning trajectories and ending trajectories. All right, so let's get rid of these existing annotations first. And they mentioned that some trajectories are discontinuous here because, for example, this one entered, but then it stopped showing up anymore here. The same applies to these. So we are looking at, according to their words, beginning trajectories and ending trajectories. So these are the ending trajectory that I just annotated here. So this one entered and then stopped showing up anymore. And let's look at the description here. It says this is the second lane. So what is possibly happening is that there are vehicles, these vehicles that entered this second lane from either lane number 1 or lane number 3, or lane, 1 or 3 is possible because this is a 4-lane uh, road. So from lane 1 or 3, they entered to lane 2. We don't know which one, but we know that they have changed lanes into this one. Um, and then because they were in lane number 2 here, they then moved to either lane 1 or lane 3. That's why they stopped showing anymore. Now for the those were the ending trajectories. For the um, entering trajectories, here is one. So this one did not show up before. We don't know what lane it was before, but now it is at about 150 meters and 320 seconds. It is now in lane number 2. So this is the beginning trajectory. and it had either changed from lane 1 or lane 3 to the second lane. So I think that's the answer. Let's see what the answer is. So here it says beginning trajectories, lane changes 3 to 2 and 1 to 2. That is correct. They are either coming from lane number 3 or lane number 1 to lane 2. Ending trajectories, lane changes 2 to 3 and 2 to 1. So that's correct. Now the final question. Estimate the wave velocity, W, at which cues behind traffic lights set into motion. So when I was looking at this question, I looked for the term wave velocity, and interestingly, so far in the book, this term has not appeared. We have not studied wave velocity at all. So I think this refers to the propagation velocity that we discussed before, which is what is happening against the traffic as the traffic jam appears. So I think this is exactly what they are asking for here. Estimate the wave velocity at which cues behind traffic lights set into motion. So if we look at these trajectories, and if we look at this traffic light, we know that the wave that is made here would be something like this. So if we have the gradient of this line, that gives us the propagation velocity. So I guess the wave velocity, that term is used when we are discussing traffic lights. Before, when we discussed propagation velocity, it was for highway traffic where we don't have any traffic lights. So let's see their answer. So here they say wave velocity is minus 60 meters divided by 10 seconds. In the brackets, they have sequence of the first 8 starting vehicles between 380 seconds and 390 seconds. The 380 seconds is here, and 390 is in the middle. So between these two time points, they're looking at the first 8 entering vehicles. So they're likely looking at these. So at 380 seconds, we have 1, 2, 3, 4, 5, 6, 7, and 8. These are the 8 vehicles that I think they're referring to. And for that, they say minus 60 meters divided by 10 seconds. So this is the 10 seconds that they have mentioned. This is 390. So this is 10 seconds. And the distance from this point to this point is that 60. So if I draw a line here,
240.
that's 240. And then this one is
180 something.
180. So that would be, yeah, 60 meters. So talking about the propagation velocity because of the traffic light upstream. Vehicles have stopped, and because when the first one stops, the second one stops, and so on, 8 vehicles stop between 380 to 390 seconds. And so I think if we draw that line, that's this line. And so we are essentially looking at this distance of 60 meters between 380 to 390 seconds. This is the gradient of this line that is connecting this traffic jam that is happening. And that gives us the propagation velocity or the wave velocity, new term, that comes out to be minus 21.6 kilometers per hour. Okay, so any questions before we go to the next chapter? We have less than 30 minutes now. So the next section here we're not covering as we discussed before because the questions here are about bicycle trajectory data, which deals with two-dimensional variables like density and so on that we have not covered yet. Okay, so next chapter is about floating car data. Before we dig into this, let's quickly review what we have learned about trajectory data. We have learned that trajectories, like we've seen here, either from traffic lights or from highway, we get information about a particular location. So in this example that we are looking at, it's between about 0 to 350 meters. That's the delta x that we have. And the time interval that we have is about 100 seconds between 300 to 400. So we have a particular delta t and delta x, and we are looking at one lane at a time. And we are looking at all the trajectories, all the vehicles that enter that particular lane and leave either within this spatiotemporal region or they don't leave and they continue to complete the delta x. So that gives us a lot of information about their position, headway, speeds, and this seems to be an ideal data. If we can get this, we know a lot about traffic. Let's see what floating car data is about and how is it different and similar to the trajectory data. So the floating car data and the in the book the acronym that is used is FCD. So whenever we see that, that means floating car data. And then there's also XFCD, which indicates extended floating car data that we'll see in a moment. Floating car data is captured inside vehicles that are traveling with traffic. So instead of looking at vehicles from a camera, either by putting a camera at the top of a tall building or using a drone, unmanned vehicles that was mentioned in the trajectory chapter, we are looking at the data obtained only from a single vehicle at a time. And we call that as floating car data because we are assuming that the vehicle is floating within that traffic. And so the main data that we get out of it is time-stamped geographical positions. And this is possible through the technology called as GNSS, which is Global Navigation Satellite System. That includes GPS, Global Positioning System, and smartphones as well. So everyone now who is traveling in a car, they carry with them mobile devices, one or more. And so smartphones provide their own data, as well as the Global Navigation Satellite System, GNSS, provide data, and it is time-stamped, so we get geographical positions, which is indicated either by northing and easting. Northing and easting is geographical way of giving you coordinates of where exactly you are on Earth, or it could also be projected in a particular geographical projection system. So without going into the details of what those projection systems are, we know that we get the information about vehicle's location at using the geographical coordinates. And we are doing that for one vehicle at a time. But if we have hundreds of thousands of vehicles traveling at the same time, all containing GNSS technology as well as smartphones, which everyone does now. Just like Google Maps, we get all of that floating car data information right in front of us when we are trying to navigate and we see that a particular stretch of a road is congested. How do we know that? Through that data that is coming from these floating cars. And floating car data can also give us travel times and speeds of those vehicles in detail. Now let's look at the data characteristics. Floating car data contains time-ordered list of geo positions. So as I mentioned before, those could be northing and easting, which tells us geographically where you are on Earth. But an additional context here is that these are time ordered. So we know the sequence of the points. So these FCD characteristics are determined by the following parameters: time or fixed interval, where we get a temporal resolution with typical values of 5 to 10 seconds. So every 5 seconds, we get a new coordinate, or every 10 seconds, we get a new coordinate. And so they are called as GNSS fixes. GNSS fixes means time stamped positions that I've highlighted here. So here's GNSS fixes, and in the later part of the chapter also, they use this term again and again. So keep in mind that means time stamped positions of the vehicles. In the context of live traffic applications like Google Maps, we also look at the upload interval. So how quickly is the position uploaded? And here they mention that that's typically 1 to 2 minutes. And we will later learn that it takes that much time because of algorithms that are used. Um, and then if you have fleets for commercial driving, you could have truck fleets, for example. So if you are collecting the data using devices of your own, then here they say that fix and upload parameters usually vary between fleets and are next to other characteristics specific for the supplying organizations, such as automotive, fleet management, or internet companies. So depending on who is managing the fleets, how much, uh, how many number of cars or trucks they have in those fleets, they have different um, values of those time intervals of how quickly they get the data. Here's an example where they have annotated different locations A, B, C, D, and E. And the heat map here, the colors indicate the number of recorded positions. So yellows and reds indicate a lot of positions, and blues indicate less number of uh, data points that are coming from floating car data. They also mentioned that vehicle type uh, can be obtained from this data as well. For example, trucks and taxis are typically less representative than passenger cars when you get the floating car data. Because for trucks and taxis, they generally, those are fleets of private companies and they have their own information. But we mainly get floating car data publicly from Google Maps, which is mostly about cars. Uh, you can get floating car data, as you mentioned before, from different device types. It could be from mobile phones, portable and in-dash navigation devices, or they can also be obtained from connected automotive systems. Uh, these days, the new vehicle models have connected technology where they share data with each other as well, and all of that data is available to the manufacturer of those vehicles, and you can also get those data for yourself for your own vehicle if you want. The mode of transportation is crucial for interpreting that floating car data. So you could have motorized vehicles, bicycles, pedestrians, depending on what you're using. For example, with smartphones, uh, that mode could be easily obtained because smartphone speed can tell you if this is a pedestrian who is moving or if it is a vehicle. And You can also get information about buses, streetcars, and trains. If you use your smartphone and you are traveling through a bus or tram, then obviously your information, the mode of the transportation, can be interpreted depending on the speed of the car or speed of the vehicle. Um, Next section is floating car versus trajectory data. So as we discussed before, trajectory data is providing us with a lot of information, but here they say that it is not possible to measure extensive quantities such as traffic flow and density from floating car data. We do get extensive quantities from trajectory data, but we cannot do that from floating car data directly. It is not possible to determine the lane from the floating car data. And then for trajectory data, we cover a minimal fraction of the road network because we are only looking at a particular delta x. But for floating car data, that particular car could be traveling on the whole road network in a given day, and we will get that information for only that vehicle, but we'll get the information for the whole network as much as the vehicle kilometers are there covered by that vehicle. So floating car data is scalable. If you can add more vehicles or with smartphones, everyone is using them, you can get more data. So FCD are nowadays often the basis of commercial routing and traffic management applications. There are many companies. We know about Google Maps, but there's also TomTom. There's also Here, HERE, which provide floating car data. You can get that using their APIs. Some of them have free tiers as well. And some of them are, if you want to get, for example, historical traffic data, for that you need to pay and use a paid tier. Next is extended floating car data. Any questions before we go to this section? All right. Um, Extended floating car data will enhance the current floating car data with more information. Okay, let's go back. So we have discussed GNSS devices and mobile phones that provide you with geopositioning. So far, the data that we are getting from floating car is just time-stamped geopositioning. But if we want to extend it, we can also get data from vehicle, from its acceleration and gyro sensors that will give us information about what is the vehicle speed and where is it headed to. We can also use radar if it is implemented or mounted on the vehicle, then it will give us the distance to and the relative speed of the leading vehicle. These two variables, by the way, are really useful for car following models. We need to know what is the distance to the lead vehicle and what is the speed difference from the lead vehicle. If we have a radar mounted on the vehicle, we can get that information. This is exactly what the autonomous vehicles also use. And if we have camera mounted, then we can also understand and recognize the road signs using machine learning algorithms. And we also understand what is surrounding the vehicle. We can also get further information, for example, position of the gas or brake pedals, activation of the turning signals, rotation angle of the steering wheel, and a lot more data using the CAN bus algorithm. So CAN bus is actually not an algorithm, it's a communication interface I highlighted here in the footnote. It's the controller area network, and all vehicles have this. And this communicates the information as time series from the vehicles. So we can get that information as long as we are extracting this. This information can be provided with the geopositions, and that makes this extended floating car data. Here's an example. We have two parts of this figure. On the left, if you look at the x-axis, this is the distance east from the start, and on the y-axis, it is a distance north. So northing and easting, these are geographical coordinates of the vehicle. And we also see colors for this trajectory, which indicates the speed of the vehicle. And looking at this diagram, it seems that this is on an interchange or some part of a road network where we see that initially the speed starting from the top left is higher, so between 80 to 100 uh, kilometers per hour, and then it slows down. It enters that loop where it has smaller speed between 40 to 60, and then it increases speed again as it enters the main part of the highway. On the right, we see x-axis contains time, y-axis there are two. There is a speed axis on the left and acceleration on the right. The dashed line that we see here indicates the speed. So this is the speed of that same floating car, and there are two accelerations, A1 and A2. So we've highlighted here A1 and A2, which indicate the acceleration of the different edges of a mobile phone. So because smartphone is used inside that vehicle, we are further extending the floating car data by getting information from the phone. Now, phone has two edges, as we know. It has a longer edge and a shorter edge. The longer edge has its own acceleration as the vehicle is moving, which is indicated by A1, which is approximately equal to 0.25 g. G here means 9.8 meters per second squared, which is the acceleration due to gravity, plus AX. So this is AX now indicates the longer edge. AY indicates the shorter edge. That gives us A2. So we have these two accelerations corresponding to the longer and the shorter edge of the smartphone device. One important thing that they mentioned here, that if we use data fusion, which means that all the data that we are getting and for the floating car data, including the extended floating car data, plus if we also get information about trajectories, we can combine these, and this is called as data fusion. So if you combine different sources of the data and correct them, then you get a much more accurate picture of the traffic flow. So here they mention combining the information by applying fusion methods such as Kalman or particle filtering. One can estimate the vehicle's trajectory more accurately than either sensor could provide on its own. So by either sensor, they mention GNSS and the smartphone. So we get information, same information from both, but when we apply these filtering methods, then we can actually get an accurate picture of the floating car data when we fuse the data. So here we get in part A and B. Part B is actually the GNSS fixes only, and part A is from the German motorway A5 using the TomTom source. So TomTom is using floating car data. So we get information about the same location by using two different types of sensors, smartphones as well as GNSS fixes. If we combine them, if we fuse them, we get better results. All right, 5 minutes to go. We are going to quickly cover map matching, and then the second part of this chapter will be covered next week. Okay, so map matching is a challenge here. Map matching is the procedure for assigning recorded geographic coordinates to a digital map as logical model of the real road network. What does that mean? Let's look at an example. Here we have a road network, and we are getting data from floating car. Now, the goal here is to accurately get the path that the vehicle is taking. We get these 3 points from floating car data, A, B, and C. And if we only take the geographic coordinates that we directly get and we plot it on top of this map, as we see here, it gives us a possible path, which is actually not possible. It is not a plausible path because we know, um, if I draw on top of it, we know here that this is the point where the vehicle can enter, and then it can take this loop and then exit from this point. We get 3 points from floating car data, A, B, and C. So this path is only possible if you are already entered the loop. If you are here, then you cannot enter the loop. You can only go on this highway. So using only the geographic coordinates that we are getting, GNSS fixes, those are not enough. We need to use algorithms to process this data so that we get the problem of map matching solved, which is to properly get the actual path that the vehicle is taking. Again, map matching is the procedure for assigning recorded geographic coordinates to a digital map as logical model of the real road network. So we should consider both the geographic coordinates as well as what is the actual road geometry. So there are two different algorithms that are used for different applications, real-time and offline algorithms. One algorithm that is mentioned here is hidden Markov model, HMM, where the hidden states are what are the possible road segments? Where will this vehicle go next? So is it on the road segment R1 or R2? And will it go to R3 next or R4 next? Those are the two questions that we have. The first probability mentioned here is the emission probability. Emission probability for each road segment, probability of Z given Ri, gives the likelihood that the measurement Z of t would be observed if the vehicle were actually on road segment Ri. So Z of t is location points, Ri is the road segment. So we are looking at the probability that the measurement of the geographic positions that we got, the locations that we got, is it possible that we get these locations if the road segment was R1? So what is the probability of that? What is the probability of having these geographic coordinates if the road segment is R2 instead? So that is the emission probability. And I think this is where we should stop for today. Any questions about the emission probability? This is one problem in map matching that the algorithm needs to solve.
I think it's better to revise it next class when we start.
Yeah, for sure. I'll start with that. So we discussed trajectory data last time, and we have started looking at floating our data. Next week, we are going to cover the rest of this chapter, hopefully. And then in the following week after that, we'll cover the exercises for this chapter. So far, we did not get into any practical formula or calculations yet, but next week that is coming. All right. Thank you, everyone,
And
for joining.
one,
And
one
yeah,
thing before you go is I have cracked the wave velocity. It's the shock wave theory. It's based on the shock wave theory. So
yeah,
whenever the lights are going to stop or it's going to turn red or green, there is a shock wave that's going to be either forward or backward. So that's what. the question was requesting for the wave velocity.
Yeah, thank you so much for mentioning that. I think in the book, at some point, there is a full chapter for estimating shock wave velocity. But it's interesting to see that wave velocity is mentioned here without actually defining it before. I guess this is coming from the second edition. In the first edition, I think this was not mentioned initially. But interesting to see that we have covered propagation as well as wave velocity without knowing much more about both. So we'll eventually see what they are and how they are calculated. Again, thank you everyone, and I'll see you next week.
Okay, see.